Hello everyone, my name is Arvin. Welcome back. Let's keep talking about area between curves. In the previous two lessons, we have talked about the concept of area between curves and the routine to solve the corresponding problems, and we have practiced two examples. And at the end of the last lesson, I said that we need some technique in order to simplify our calculation. So in this lesson, I will show you some techniques. Okay. During the previous lessons, we have already known that if you are given a graph of y equals f of x and the graph of y equals g of x, and you are required to calculate the area enclosed by the two graphs and the corresponding intervals, the corresponding vertical lines. So first, with a problem of this kind, there is a routine that firstly you determine the area differential for an arbitrary vertical slice, and then you further integrate the area differential over the interval x equals a to x equals b. Then you arrive at the exact area of the yellow region by some simple calculation. The calculation part is straightforward, but as we know, mathematics is not only about methods, but also about the specific calculation. We must try to get the correct number, the correct answer. So that is also important, which will determine how much score we can obtain in our exam. So in order to speed up the calculation, we must be familiar with some of the methods I'm going to show. For example, find the area of the region bounded by the graphs of y equals 2 times the square root of x, y equals 0, and y equals 3 times the square root of x minus 5. For this problem, let's firstly draw the two graphs. Okay, they are shown here. This is a graph of y equals 2 times the square root of x, and this is a graph of y equals 3 times the square root of x minus 5. So this curve touches the axis at x equals 5. Clearly, the region of interest is shown here, is shaded in yellow now, and as before, as usual, we need to determine firstly the points of intersection, which will be our limits of integration. So to do that, we set the equations to equal to each other and square both sides. And we subtract 4x from both sides and add 45 to both sides. We finally arrive at x equals 9. So this is the x-coordinate at the points of intersection. If we want the y-coordinate, we may come back to either of the equations. Simpler of the two, the first one, y equals 2 times square root of 9. We simply plug in the numbers. Then we find y should be equal to 6. And this tells us that the y-coordinate for the points of intersection is 6. But in order to ensure that our result is accurate, so with better. So I usually suggest that you also plug the number x back into the second equation to check. Let's check. X equals to 9. So this is going to be also 6. So it's highly possible that our result is correct. Then we can proceed from here. The other limit is clearly 0. The other limit of the integration is clearly the 0 here. But the question is, we soon find that towards the left side of the region, when you look at a typical vertical slice, the top of that curve touches the graph of y equals 2 times the square root of x, and the lower bottom touches the x-axis. However, toward the right side of the region, there is something different. The lower bottom of the vertical slice now touches the curve of y equals 3 times the square root of x minus 5. Okay, something different from previous examples, because this time, for different region, the vertical slices, the area differential dA will be expressed in different forms. And clearly the cutoff point is x equals 5. So, in order to calculate the whole area, we must now break the whole region up into 2 pieces. So, in order to calculate the region, the area of the left region, we integrate from x equals 0 to x equals 5, the area differential, which will be 2 times the square root of x dx. That's the length of the slice in the left region. And in the right region, for the area of the right region, we integrate from 0 to 9. From 5 to 9. The vertical slices, the area differential dA is going to be the top curve, 2 times square root of x, minus bottom curve, 3 times square root of x minus 5 dx. So, okay. It's straightforward to find out the antiderivative of each integrand and then calculate the final result. It's simple, but there are still simpler methods available for us to calculate the total area. So now let's look at another method. So till now, everything is the same as before. But now we see that by applying the methods we introduced before, we have to break the region into two pieces. But now I will show you a method that this is not necessary. Okay, we have introduced the concept of Riemann sum by dividing the region into vertical pieces, vertical rectangles. But it's not required that the rectangles have to be vertical. They can also be horizontal. Okay, and you can easily find that if we use horizontal slices to represent the total area, then we don't need to break the whole region into two pieces, because this time the vertical slices, the area differential, the area of the vertical slices are never the same among the whole region. So it means the vertical slices are basically the same area inside the region. This time, if you want the area differential, it will be the length of the slice. This time, the length of the slice is going to be the x-coordinate on the right minus the x-coordinate on the left. That will be this x-value, the x-value of this point minus the x-value of the point on the left curve. So this time we don't care about a top curve and bottom curve. We care about curves on the left and curves on the right. So it's straightforward. It's almost the same idea. So if you rotate this picture about the origin by 90 degrees, you will find that the horizontal slices are the same as the idea of vertical slices. So indeed, the calculation for the vertical slices part applies the same very well to the vertical slices method. So that but the only difference this time is that we have to express the curves in terms of y, because we are going to integrate along the y-axis now. So to do that, we are going to express the curves, express the functions in terms of y rather than x. So we need to solve for x from the original equations. For the first equation, we square both sides and find x to be 1/4 y squared. And for the second equation, we also square both sides and divided by 9 from both sides, and add 5 to both sides. We arrive at x equals 1/9 y squared plus 5. So this is what we are doing. For the horizontal slices, we still look at the horizontal slices. We integrate along the y direction. To do that, we have to re-express the curves in terms of y. So x is now a function of y. Then we are going to integrate all the area differential to obtain the area of the yellow region. Okay, now everything is the same as in the previous examples. So we need to integrate, but the only difference is that we need to integrate over the y-axis rather than the x-axis, because this way we can simplify our calculation in that we can express the area differential with a single formula rather than breaking the area into two parts. So the calculation process is straightforward. Look, the y-coordinates for our region of interest extends from 0 to 6. So the limit of the integral is from y equals 0 to y equals 6. And the area differential is expressed as the y-coordinates on the right of the x-coordinates on the right, which is 1/9 plus 5, minus the x-coordinates on the right, which is 1/4 y squared. So that is going to be the length of the horizontal slice, all times dy. Okay, this is the area differential now. To be integrated over the interval between 0 and 6. Okay, now the calculation is also simpler. To anti-differentiate each term, we find the antiderivative to be 1/3 y. Okay, 1/3 y. Okay, maybe we should simplify first, because we can collect the terms. It's a good idea to first collect the terms. So I'm sorry, I'm going to scramble off this. Okay, rub off this part. Let's firstly collect the terms. So how do we collect the terms? Because y squared can be collected. So it's a 1/9 minus 1/4, which is going to give you 5/36 y squared minus negative, plus 5 dy from 0 to 6, and we may factor out 5/36. Factor out 5/36 is going to be 36 minus y squared dy, and we can always take this constant outside this integral. Then it's going to be now the antiderivative is clearly 36 y minus 1/3 y cubed to be evaluated between 0 and 6. Then finally, we have the value at 6 for the, and at y equals 6 for the antiderivative is 116 minus 144, and this is going to be 72. So the final answer is 20. So that is the exact region, the exact area of the yellow region. So to summarize, in order to avoid breaking the whole region into two parts, we choose to integrate with respect to y. We choose the area differential to be horizontal slices rather than vertical ones. So from this example, we can master the principle of area calculation. So it doesn't matter how you calculate, how you integrate. It only matters is the integral you do the really the area of the region or not. So integrate the area differential to integrate the horizontal slices provides a new method for us to simplify our calculation in the future. Let's look at two more examples. The first one, find the area of the region bounded by the graphs of y equals 0, y equals x squared, and y equals x to the fifth power two ways. Okay, here by two ways we mean by integrating with respect to x and by integrating with respect to y respectively. Firstly, let's look at the two curves, and the point of intersection is clearly their region and 1, 1. So it seems that we can integrate with respect to x. That means we are looking at the vertical slices here. Okay. The top curve, this is the arbitrary vertical slice. The top of that slice touches the upward opening parabola, and the down and the bottom of that curve touches the fifth degree curve. So it seems that we do not have to break the region into two pieces. So the calculation is straightforward. The total area is going to be the integral from x equals 0 to x equals 1 of the area differential, which is top curve minus bottom curve times dx. Okay, the calculation is straightforward. The antiderivative is 1/3 x cubed minus 1/6 x to the 6 to be evaluated between 0 and 1. And plug in x equals 1, we have 1/3 minus 1/6 and minus a value at 0, which is clearly 0. So we finally have the area to be 1/6. So that is the first method. Here we have use the vertical slices. We are integrating with respect to x. Now let's look at how we can integrate with respect to y. Let's firstly look at the horizontal slice here. This is also an arbitrary horizontal slice, and the length of that slice is going to be the x-coordinate on the right minus the x-coordinate on the left. But before anything, since we are going to integrating with respect to y, so here we have to express everything in terms of y. So we firstly solve for x from the first equation, which gives us x equals the square root of y. And for the second equation, we have x equals the fifth root of y. Then, okay, they are showing here. Now everything is easy. we find that the x-coordinates of the region extends from the origin 0 to 1. So the integral proceeds straightforward as the integral from 0 also to 1 of the length of the horizontal slice y to the 1/5 minus y to the 1/2 all times dy. Okay, this time let's also anti-differentiate each term. So the antiderivative of y to the 1/5 is 1 plus 1/5 y to the 6/5. And the antiderivative of the square root of y is 1 plus 1/2 y to the 3/2. That is going to be evaluated between 0 and 1. So plug in y equals 1, we have it's 5/6 1 minus 2/3 1. Okay, this is the value of the antiderivative at y equals 1 minus that which is clearly 0 at y equals 0, which is going to be also 1/6. So bingo here. Two answers coincide even though we have calculated the area in different ways. So good thing, good news. So maybe if you are so powerful, you want to check whether your answer is right. So in the exam, you can always do that. But I really don't suggest. Try to do things right at one shot. Okay. Okay. Now let's look at the last example. Find the area of the region bounded by the graphs of y equals 3 times 1 minus x squared and y equals 4 times 1 minus x squared squared. So before drawing the graphs, since you guys must have learned parabola, quadratic functions from secondary school, so you should try to think out how can you plot this parabola first in your mind. So the first question, what is the vertex of the parabola? Okay, the vertex lies on the line of symmetry, so it should be 0, 3. And what are the zeros? The zeros should be x equals positive negative 1. Okay, so from these 3 points, we can determine the shape of the parabola. It's going to be like this. Okay, with the 2 zeros and the vertex, we can draw that parabola. Okay, then look at this. It's a 4th degree curve. If you open the bracket, it's going to be a quadratic function, of course. But how can we draw this? We also find certain points before guessing what the shape can be. Okay. Clearly, it has 2 zeros at x equals negative 1 and 1. Look, you can just plug in x equals negative 1 and 1 back into the function. Y is going to be 0. So those are 2 zeros. So what is the value of the function at x equals 0? It's easily calculated. At x equals 0, it's going to be 4. Okay, now we have 3 points in total, and we can see that this must be an even function of x. So it's going to have a symmetry about the y-axis. So we may draw this graph this way. Okay, that's how I guess the shape of the function is going to be like this. So the computer gives us the shape of the 2 functions, and Okay, for the two curves, there are 4 points of intersection in total, and 2 of them are the common zeros of these two graphs, and the other 2 are to be determined because the curves of the two functions look. Firstly, at this region, the up curve is going to be the 4th degree function, and the bottom curve is a parabola. And when crossing this point of intersection, the top curve and the bottom curve exchange their positions. So we must determine this point of intersection because during different parts of the region, we need to express the length of the vertical slices in different ways. So in this case, is not that in this case we also have to break the integral into 2 parts, but it is not. But this time is because the 2 curves exchange their position as the top and the bottom curves. So that's why I show the example here. So okay, I hope that in the future, whenever you find that you cannot express the area differential in a single expression, just don't hesitate. Try as quickly as possible to break the region into pieces and to do the calculation as soon as possible, because time is usually very precious in your exam. So when you find you have to do this, just try as quickly as possible. Then how do we determine the points of intersection? For these 2 points, again we have to set the 2 equations equal to each other. It's 3 times 1 minus x squared, which is going to be equal to 4 times 1 minus x squared squared. So since we are looking for points of intersection other than plus and minus 1, so we might divide through both sides 1 minus x squared. So that is going to be 4 times 1 minus x squared. And rearrange terms, 4 times x squared is going to be 1. So x squared is going to be 1/4. Then we finally find the points of intersection. The x coordinates for the points of intersection to be plus and minus a half. Which is shown here. Now we can do the computation. But before we really do the computation, there is also a method. There is also something we should notice. Since all the curves are even functions in terms of x, so the region of interest, which are shaded in yellow here, have a symmetry around the y-axis. So the area on the left part should be exactly the same as the area on the right part. This way, we may only calculate the area in the right part only, or in the left part only, then multiply by 2 later. So we may integrate from 0 to 1. This is half the area if you integrate from 0 to 1. And the other half, the integral from -1 to 0 is going to be the same as the area on the right side of the y-axis. So, but be careful. Is integral from 0 to 1 right? No. We find that we have to, again, divide the integral into 2 parts. Firstly, for the subregion, for the first subregion, for the left subregion on the right, we need to integrate from 0 to 0.5. And the area differential is going to be, let me just take a look. It's 4 times the square of 1 minus x squared. 4 times the square of 1 minus x squared. Minus, this is top curve, minus bottom curve. The bottom curve is going to be, just take another look. It's 3 times 1 minus x squared. Okay, top curve minus bottom curve, Azura, all times dx. And for the second subregion on the left, on the right, for the second subregion is going to be integral from 1/2 to 1 of the area differential. Now the integrand will be the negative of the first one, because the bottom and the top curve just exchange their positions. So it's going to be the negative of the first integrand. Okay, exactly the negative of the first one. Okay, so dx. Then here it seems that we have to open the brackets now, though it can be a little bit tedious. So for the first bracket, we open the bracket as, okay, times 4. This is the first part. So we pick up firstly the first degree term is 4x to the 4th power. The negative 2x squared is going to be multiplied by 4, so we have a negative 8x squared. But looking at the second term, this is going to be added by 3x squared, so it's going to be minus 5x squared. And for the constant term, from the first term we have 4, and from the second term is plus 3. It's minus 3, so the constant term is 1. Okay, be careful. Always be careful when dealing with this tedious calculation. The highest order term, 4 times x to the 4th, and the second term, negative minus 8 plus 3 minus 5. The constant term, 4 times 1 minus 3, so it's going to be 1. So here is the integrand rearranged. Okay, when you need to be careful, you must be careful. And when you need to use techniques, you can use techniques. For example, we have spent the effort to very carefully examine this term, this integrand. And for the second integrand, you don't need to open the brackets anymore, as long as you notice that it is exactly the negative of the first integrand. So it's going to be negative 4x to the 4th power minus 5x squared plus 1 dx. Okay, now let's antidifferentiate. The antiderivative is going to be 4/5 x to the 5th minus 5/3 x cubed plus x. Okay, it's going to be evaluated between 0 and 0.5 plus. Here also, since the integrand is a negative of the first one, the antiderivative is also exactly the negative of the first one. So do what you do carefully, and use techniques to save your time. So this will be the negative of the first antiderivative. (0.51). Okay, that's it. Okay, why not have a check whether it is right or not? You better check before going on. X to the 4th power will give you a denominator 5, and the exponent is going to be 5. And for x squared, denominator 3, and exponent 3. And for 1, it's going to be x. Okay, good. Sounds good. Looks good. Let's proceed. So the value at a half is, for the derivative, the value at a half is 4/5 it's a half, and to the power of 5 is going to be 1/32 minus 5/3 1s plus 1/2 minus the value for x equals 0, which is clearly 0, plus, how about this? The value at 1 is going to be negative 4/5 minus 5/3 plus 1. Okay, we can cancel this plus here. Okay, then look, we are now calculate this integral, independently from that integral. So here the plus means the sum of two independent integrals, and here the minus comes from the antiderivative itself, and is going to minus, it's going to minus the brackets at x equals 1/2. So the minus gives you plus, so it's going to plus the value at 1/2, and plus the value at 1/2 is exactly this term. So we may just save the effort and put 2 times this thing in the very beginning. Okay, that's it. So now let's proceed to do the arithmetic. Okay, it seems that I need to okay, let me check if I can do this. Okay, not possible, so I cannot pass. Then okay, let's do the arithmetic. Okay, maybe just proceed from here. So firstly, for the first term, if 2 times 4 and 2 times 4 gives you 8, 8 is a factor of 32nd, so it's going to be, for the first term, it's going to be 5 1/5, and the new denominator is going to be 1 reduced with 8 is going to be 1/4 minus, here is 5/3, and 2 is going to cancel with this 8, and 2 is going to cancel with this 8, is going to be this reduced to be 1/4, and 2 with this 2 is going to give you 1, and minus this is 4/5 plus this 5/3 minus 1. So minus 1 and minus 1 cancel, and then and then we need to find a common denominator now. The least common multiple of the denominator are going to be 60. So it's going to be 3 for the first fraction. The denominator for the first fraction is 3. For the second fraction is going to be 25. For the fourth is going to be minus 48, and for the last fraction is going to be plus 100. Okay, now let's be careful. Proceed this calculation. 3 minus 48 is going to give you minus 45. Minus 45 minus 25 5 is going to give you minus 70. 100 minus 70 is going to give you 30. So it's 30 over 60. Then finally, it's going to be exactly 1/2. And remember, it's only half the area, so the total area A is going to be 2 times 1/2, which is going to be 1. Okay, very good. Finally, we have finished this lesson, and I also missed a call during this lecture. Okay, so I hope that from this lesson you may realize that sometimes the very general formula cannot solve anything. So you should be clever to apply that general formula into specific cases to make adjustments so that you can calculate the area more efficiently, more quickly. And in this example, we need to firstly break the integral into 2 parts. Okay, for each part, we use 1 integral because the top and bottom curve exchange their positions for different subregions on the right. And also because this is one thing, and another thing is there is symmetry around the y-axis, so we may apply that symmetry, take advantage of that symmetry so that we calculate only half the area on the right and then multiply by 2. This saves time. And during the specific calculations, for example, during the specific calculation, for example, here, when writing down this integrand, and for the other is exactly the negative of the first integrand. And also, when doing simplification, you don't need to do the simplification for the second integrand because just use the property because the second one is exactly the negative one of the first. And also for the antiderivative, is also exactly the negative of the first one. So this helps save the time. You don't need to do the same thing twice. Okay. Then also, for the specific calculation, when you have to minus 0.5 here, maybe you can just multiply 2 in the very beginning because they are exactly the same thing. So this also helps you save time because doing the calculation of product is also either than the calculation of adding up things. Okay, so also I also a word of warning, you should really be careful with these specific calculations. So make sure you are right at the first shot and don't count on coming back to exam whether you have calculated right previously for previous questions. So when you do this question, you know how to do that. Make sure you do it right at first time. So don't worry about that when you proceed to calculate to dealing with other problems. And also, this is the last example. And for the example, okay, even though we are deal with the first calculation, deal with calculate the area with integral respect to x-axis. But so in order to show you an example, I show you that you can also calculate the area by integration with respect to y-axis. So you may always choose to do things in different ways, just to the way you find more convenient for you. And also for this example, sometimes we have to break the region into 2 parts if we use vertical slices. So it's a good idea to change your perspective into integration with respect to y, so that you can express the integral in one formula, in a single formula, rather than divide the whole region into 2 parts. Okay, very good. So that's it. And sorry. Okay. And I'm sorry. So at last, I have to say that thank you for watching this video, for listening to this lesson, and I hope that in the future, if you want any tutorial, you can contact me through QQ or WeChat, and it depends on your need, so that we can arrange the lesson in different fashions. And okay, that's all for today. And okay, best wishes and happy new year. Good luck. Okay, goodbye.